So just to give you a quick overview of the application space for quantum computers, um, there are four main application areas. There are actually many application areas for quantum computing, but I'd say that these are the most mature and well understood at this point. I've arranged them in chronological order in terms of feasibility. We believe that chemical and material simulation is the nearest term application, followed by machine learning. The next one is optimization and search, and in the longer term, we believe that linear algebra will be an exciting application area for quantum computers. And so what I'll do is I'll go through each of these application areas and give you a little bit of sense of what's going on in them and what quantum computers can and can't do in them, so you can understand how it may impact digital twins. If we look at the digital twin stack, I think of digital twins as having two kinds of stacks. One is an operational stack where you have a physical twin, and you have then sensors and controls that interact with the physical twin directly, a network that carries the data commands to and from the digital twin to the physical twin, a data layer where everything is pulled together. Once you have a data layer, then you can have visualization and dashboards. And then once you have this, then you start to look at things like find analytics and insight in the data. And then once you find some insight, usually there's a decision, some simulation, some optimization. The other digital twin stack that I think of is one where there is no physical twin because you're developing it. And so there's no physical twin, and what takes the place of that is a simulation layer, which follows a visualization is built upon that. Again, you have analytics and insight and some decision and optimization step after that. Where these four quantum application areas can apply is in the operational stack. I see quantum machine learning being able to help with driving analytics and insight in the data. And I see quantum optimization, machine learning, and linear algebra operating at the decision, simulation, and optimization layer here. On this side, I see simulation layer being accelerated by quantum algorithms in chemical and material simulation and in linear algebra. And in the analytics and insight, again, quantum machine learning, and decision and optimization, again, quantum optimization and quantum machine learning. And let me say, if anybody has any questions, please feel free to interrupt me. It's usually easiest to answer the question when the slide is up. And I have about 30 slides for about 30 minutes. So okay.
If I
Yes.
might interject the first
Yes,
question.
please.
What you think the first port of entry, or let's say minimal viable product for quantum digital twins, if we consider this five purple
the minimum viable minimum viable product. Well, I would say the two nearest application areas would be chemical and material simulation and the machine learning. And I can think of a couple of ideas where a quantum machine learning might be applied. For example, I'll show you an example in fault detection and classification.
But you answered my question for time being.
Okay.
Thank you.
Okay, good. All right, good. So let me start with quantum machine learning. What we know about quantum machine learning is that quantum machine learning models can see patterns in data that classical machine learning cannot. We published this paper back in 2021, and we demonstrated with a particular data set, the discrete log data set, which is important for cryptography applications, that a quantum computer, a classical computer cannot see any pattern with this, and we're pretty confident on that because after, I don't know how many decades of RSA encryption, nobody's figured out a pattern in the numbers. Whereas we know that there is a quantum algorithm that can approach 100% accuracy in terms of separating the divisor in this data set. And so we know that a quantum machine learning model can see patterns in data that classical machine learning models cannot. So what does this mean? More specifically, what we're observing is that on some data sets, not all data sets, but on some data sets, we see an increase in accuracy. So here's an example from a paper published by the European Space Agency. In their data set, they're looking at satellite images, and they'd like to identify images where a volcano is erupting, such as these 4, versus images where there's no volcano erupting, such as these 5. And what they built was a hybrid quantum classical neural net. So they have a couple of layers of a convolutional classical neural net, feeding into a couple of layers of a quantum neural net, and then the output is the final classification. This is a binary classification problem. The current state of the art is a model published by Del Rosso. On this particular data set, you can see that it achieves a precision, recall, F1 score, and accuracy of 85%. This hybrid quantum classical model that the ESA proposes is here, and you can see that it has a precision, recall, F1 score, and accuracy that is 11% higher across the board. First thing to notice is that we are improving, or this model improves on accuracy by 11%. This is actually not easy to do, given that convolutional neural nets and image classification is now quite an old application area for AI, and the accuracy rates have largely plateaued in sort of the 80 to 90% area. So a 1% increase these days is considered impressive, and we're showing 11% here. Another thing to point out is that both the precision and the recall are increasing. So precision, if you're not familiar, is a metric for false positives. Recall is a precision for false negatives. Usually you have to trade off precision or recall. In other words, in order to increase precision, you have to decrease recall or vice versa. And what we're seeing is an improvement of both simultaneously. The other thing to notice is that the size of the two models, the classical model has 2 million free parameters. The quantum classical model has 40,000 parameters, so almost 2 orders of magnitude smaller, plus 56 qubits. So it's a much smaller model. And one of the things that this implies is that you need less data to train it, since you have fewer free parameters to set. And in fact, we do see that. In another paper, what you see here is on the y-axis prediction error, so lower is better, versus training set size. And we're comparing 2 quantum models, one in orange, one in blue, versus 6 classical models. Only the best of the 6 is plotted here for clarity. So the first thing to notice is that we have a quantum model that has lower prediction error than 6 classical models. But I think what's more interesting is that you can see that this quantum model is achieving the same level of accuracy as the best of 6 classical models, with approximately an order of magnitude less data. And so this actually may be the bigger deal with quantum machine learning, in that on some data sets, the sampling complexity is lower. This often is important for engineering-oriented data sets where you can't go out to the internet and gather a billion data points. Some engineer has to go, particularly in manufacturing settings, and get the data from a tool or a manufacturing line. And maybe the engineer can get hundreds, maybe thousands of data points, but not a billion, right? And so what this opens the door to is the ability to apply the power of machine learning to really small data sets. So given the fact that we're seeing an increase in accuracy on some data sets, not all data sets, and reduced sampling complexity, again, on some data sets, not all data sets, what we are focusing on are those applications where both accuracy has plateaued in classical machine learning, like image classification, as well, and still not high enough, as well as those applications where data is hard to get. And a place where both of those come together is an anomaly detection. Anomalies are by nature rare, and so data is hard to get. And what we often see in the classical machine learning is that the error accuracy rates have plateaued in sort of the 60 to 80% range, which is often not high enough to be actionable. And so a good example of that in digital twins is in fault detection and classification. And if Robert Baseman is in the audience, he and I actually worked on this together. And so, for example, here is a study published by Applied Materials, and in the study, they claim a major pain point in today's fault detection and classification systems is false and/or missed alarms. And I believe in this paper, they state that more than 50% of the alarms that are triggered in FDC systems are false positives. So you're actually chasing more false positives than real or true positives. When an alarm goes off for example, in semiconductor manufacturing. So this is a problem, and this is a reason why these alerts and alarms are not actionable, for one thing. And another problem is that you end up just wasting a whole bunch of time, assigning personnel to fix problems that don't exist. And what eventually happens is you get alert fatigue. And the folks that are supposed to respond to these alarms start to ignore these alarms. And what happens is that you start to increase the number of real positives that actually get through the system. The other thing you see is that teams will raise the alert threshold, which does reduce the number of false positives, but it also increases the number of false negatives, which is often has worse consequences. So FDC is an interesting place to apply quantum machine learning because it's an anomaly detection example. And this is a paper published by UCLA on a fault detection and classification data set. This is for rolling machinery. And you can see what they've done here is that there are these three components in a bearing. So this is an inner ring, this is the middle ring, and then this outer ring sits on the outside. They put the whole bearing on a motor. And then put a load on the bearing as well. And then they have an accelerometer attached in order to just watch vibrations coming off the system. And they have both good and bad versions of each of these elements. A good version has no line in the middle. They actually took a saw and actually cut through this material in order to create the defect. And then they put this together and they created a bunch of time traces, as you see outputted here. And they have 12 health states. They have 3 speeds, 600, 800, 1000 RPM. And then they have 4 health situations. The first one is healthy. So they're all 3 components are do not have this defect in them. And then they have 3 unhealthy states where you have one of these elements that have this defect introduced into the system. And so then they ask these machine learning models to first identify whether or not there is a defect in the system, and also then to classify what component and at what speed the defect is occurring. And you can see the classical results here are sort of in the 50 to 60% accuracy to F1 score range. The quantum machine learning model results are seen here, and you can see there's this additional 7 to 12% increase in accuracy across the board. Now, these sorts of increases, it's not uncommon in these kinds of data sets for us to see improvements on the quantum side in sort of this sort of range, 5%, 12%, 15% sort of range. And so if you start to cast this in an overall equipment effectiveness framework, where they're sort of where what we're measuring is the available time and the efficiency in which a piece of equipment is used. There are 3 big categories of problems: the availability, the productivity, and the quality. And then within each of these, there identify 2 types of losses, which altogether have the big 6 losses. I've listed here a number of quantum algorithms that could be potentially applied to each of these and give you an example here. And if you assume a quantum benefit in sort of the 1 to 10% range, say 5% as an average, 5% over 6 categories is 30%. This is 30% is the difference between typical and world-class overall equipment effectiveness. And so you can see that bringing a lot of small efficiency improvements using quantum algorithms can be quite transformative in the way that equipment is actually used in manufacturing settings. Okay, so this is my last slide in quantum machine learning. Let me just pause for a second to see if anybody has any questions here. Okay, I'll move on. Go ahead. Go ahead.
No, we have a question. Sadas, your question.
I have a question.
Yes, please.
I looked at the accuracy and precision, so it doesn't seem to be that high as I was expecting. So I'm trying to wonder whether the classical algorithms are inefficient to start with. So my question is, what is the theoretical limit of this classical algorithms in terms of accuracy? Do you know?
I don't know the theoretical limit. I can say that there's a good example in the ImageNet dataset. And the reason why ImageNet is interesting is because there's an annual contest every year to see who can develop the most accurate machine learning model in ImageNet. Maybe I have that slide. Give me just a second, see if I have it in this set.
So as you're
yeah.
looking at the slide, the follow-up question is: are these, I mean, these what you call as quantum algorithms, mainly some sort of a Fourier transform you are using, or is it something more complicated?
So there is, I wouldn't say that there is a sort of standard approach with machine learning, quantum machine learning, in terms of how it's being used in image classification. There are convolutional quantum neural nets, which I guess if there is a standard approach, that's probably the most popular one. Is it taking a Fourier transform in its model?
It seemed to me, because you are saying logarithmic data set, so I need to read the paper. So I thought if you knew the answer at the tip of your...
I don't know it right off the top of my head. I can say that in the way that the way that data is encoded in quantum machine learning models, there is a way that sort of naturally takes advantage of the Fourier transform.
That's what I thought.
I'm not sure if in the European Space Agency paper, if that's the way they encode the data, but there is a sort of natural way to encode Fourier type information into quantum machine learning models that is possible. So I guess the answer to your question is possible, but I think I would have to go back and review the paper in order to give you a more competent answer.
Thank you.
With regard to your question about the upper limit on accuracy, so this is a paper published by MIT, the computational limits of deep learning. And what they do is they look at a number of data sets. ImageNet is one of them. They look at a couple of others. And as I said, ImageNet has an annual competition. And what the authors of this paper did is they just looked at the trend in the ImageNet competition to sort of extrapolate future performance. And so what they did is they looked at the error rate. And at the time of the publication of the paper, which is 2022, they looked at how many flops it required to reach that error rate, and then they looked at the cost, and then they did an extrapolation to say, okay, for an error rate of 5%, it requires this many flops, et cetera. And so what they found is for a 9% error rate, they found it cost $1 million. And just taking that trend and using a polynomial model, they also have an exponential model which has worse results. So I took I took the polynomial model, which is a little bit more conservative. To reach 5% error rate, you need $1 billion. And to get to a 1% error rate, you need $10 to $16. So that's $10,000 trillion. And by the way, you would also emit 1,000 times more CO2 than the entire world emitted last year or 2 years ago. And so I guess there is no, I guess what this is saying is that there's no theoretical limit in error rate, but there is sort of a error rate cost curve in which where things do have a practical limit. It's actually super exponential, I believe, is what they found. And so and this is kind of what I mean when I say an 11% increase in accuracy is actually quite enormous. To go to 95% accuracy cost $1 billion, and we're seeing that in this we're seeing that kind of result here in this quantum hybrid, a quantum classical hybrid. We're seeing 96% accuracy rates on this particular data set. So and I think you have a very common reaction, which is, well, 11% is not that much. But in this regime, it's actually quite large. If you look, instead of accuracy, you look at inaccuracy, just look at 1 minus accuracy. You can see that the inaccuracy drops from 15% to 4%, which is almost a 4x improvement in the inaccuracy rate. And so this can be, this I think is quite hard to achieve. And if you think about, for example, false positives, your number of false positives drops by a factor of 4x. That could be quite impactful.
I think your point is well made, because you just made a point based on this MIT paper that it's an exponential and maybe super exponential. I'm just questioning what drives the exponential, but let me go through the papers and we can have an offline discussion later.
Okay, sounds great.
We have a few more questions.
Yes, please go ahead.
Kanat and next Henning.
Hello.
Yes, hi.
This is a very general question. It seems that many of the things you are doing is really parameter optimization. I was wondering if quantum annealing is an alternative to using, machine learning framework with generalized quantum computing.
Annealing is being used and applied to a machine learning in exactly the way you're talking about, is sort of doing some sort of parameter optimization. But let me say that there are, I think, more powerful ways to use quantum computers. I mean, this paper is not an annealing approach. It's not a parameter optimization approach. This is really a it's this, what we did here was a support vector machine with a particular feature map that was only computable using a quantum algorithm. And so what you see, these kinds of results where you're seeing essentially an exponential separation in computational complexity between what a classical computer can do and what a quantum computer can do. That's really the basis in which you're seeing this outperformance in the quantum machine learning model. So it's not really a parameter optimization approach. It's really identifying a circuit or a computation that is only really computable by a quantum machine.
I see. Okay.
Yeah,
Thanks.
Yeah. You're welcome. Yeah. Any other questions I can take? I can't see the chat from my view, so.
Charles, this is Henning Braunisch. I'm with the Smart User Institute and also Intel. My question, and I may have missed it, but how do you simulate the performance of the quantum algorithms?
So some of these, see, this I believe was done on simulator. This was done on hardware, I believe. So we have hardware in which you can actually execute.
So you're not presenting, Chuck.
Oh, I'm sorry. Thank you very much for letting me know that. I'm sorry. I did not know that. I think I did not show this slide from MIT.
Something?
Yeah,
I see.
yes, I'm sorry.
Okay.
Yeah, so I'm going to go back and show you this paper from MIT. This is the paper where they find that it takes $10,000 trillion to get to 1% error. And so to answer your question about simulability, this paper was done on simulation. And there are a number of ways to simulate quantum computers. The problem is that the computational complexity of that simulation grows exponentially. And so at some point you start having to make approximations, and at some point you make so many approximations it's no longer accurate. The way these simulations are done are typically using GPUs. There are a couple of different frameworks within that. Tensor networks is one. And so there are a couple of different approaches. The approach that makes the most sense really depends on the quantum circuit that you are trying to simulate. This paper, I believe, was done on hardware, and so there are quantum computers now where you can execute things on hardware. And our computers, the ones that we have at IBM, they're now large enough that they are essentially not simulable by classical machines. And so we're now in a regime where our computations, we have to think very carefully about how we verify the accuracy of our computations, because now we're beyond a point where classical computers can verify them.
Thank you.
Yeah, you're welcome. Any other questions?
Tim, China?
Yeah, I had a question on the Spoilberg defects.
Sure.
I mean, this is an incredibly classical problem, right?
Yes.
And the defect frequencies can be calculated from the geometries of the outer race, inner race, cage, and bearing diameters, right?
Yes.
So you can actually predict, you can calculate, I should say, exactly what those frequencies of those defects are. In the quantum case, is it able to detect where the defect is?
Yes.
Obviously.
These accuracy, precision, recall, and F1 scores are for a multi-class classification problem where they are looking at this time trace and then placing the result in one of 12 classes.
So normally in ball-bearing defects, which I've done a lot of work on, we take the Fourier transform of the time series and we get the individual frequencies, right? And we can calculate whether that frequency corresponds to a particular defect, like if there's a defect on the inner or outer race, because it's just calculated based on the RPM and the geometry.
Sure.
Is the quantum doing some type of frequency analysis to figure out where that defect is, or how does that work?
I don't think so. And the reason I say that is because from this data, what they do is they take a number of features from it. I don't recall them taking frequency features. I recall them taking things like average and standard deviation and skew and kurtosis and statistical measurements like that.
Right.
I think it would be interesting though to take your approach and do, for example, a Fourier transform and then input this and see what the results are. I have not seen that approach on this particular data set, but it makes a lot of sense. So I would say that that would be a really interesting approach to compare and then see what happens. I think at this point, nobody knows because as far as I know, no one has tried it.
Okay, thank you.
You're welcome. You're welcome. I think in the interest of time, let me move to the other three sections. Optimization of search is the next section. And so, you have this fault detection. Let's say that our system has detected a fault in a tool in semiconductor manufacturing. And then now the next step would be, okay, what are we going to do about that? A tool has gone down. In the decision making, oftentimes in a digital twin, there's an optimization step, and then you can choose, for example, the optimal option. Let me say that, first of all, let me say that classical computers are already pretty good at this kind of optimization problem where steepest descent works. The input space is continuous. You just follow the steepest gradient to find the valley, and that there's no reason for a quantum computer to improve on that. What classical algorithms are not so good at is this kind of problem on the right. That is let me get my laser pointer. The input space here is not continuous, it is discrete, and as a result, there is no, let me back up and say this is a traveling salesman problem. What you're trying to do is find the sequence of cities to travel in order to have the shortest overall total distance. There is no local gradient, and so therefore there's nothing to follow. Steepest descent doesn't work. Moreover, the solution space grows exponentially, and so you can't do a brute force search of all possible solutions. And so this is an area where classical optimization or combinatorial classical algorithms could really use some help because there are many problems that fall into this category. An example of that is production scheduling. In the IRDS roadmaps, you can calculate that wafers spend about 2/3 of their time simply sitting around at the fab and waiting, which is kind of an astounding statistic to me, given the fact that fabs cost $25 billion. If you're able to increase the throughput at a fab by 1%, so this goes from 66 to 65% wait time, you can the increase in revenue at a 5 nanometer fab would be approaching $1 billion over 5 years. So this is a hard problem. Right now, what happens is we don't do any production scheduling optimization because that is too hard to do. That's an NP-hard problem. And what we do instead is we do dispatch. We use scheduling based on dispatch rules. And the problem is something like this. Say there's 3 tools. Tool 3 has gone down because our FDC machine learning algorithm has detected a problem. We're left with 2 tools. These lots start coming in, and if you just use dispatch rules, you can get you can see where tool 1 is executing recipe 1 and 2. Tool 2 can execute recipes 1, 2, 3. These lots are coming in, they're color-coded by what recipe they need, and you can see they just start to get assigned a tool as they come in, and you may end up with something quite unbalanced like this, where tool 1 is underutilized, the total lot cycle time for all lots is almost 10 hours, and tool 1 utilization is 25%. So this is can be improved, right? If you just do a little bit of look ahead and do a little bit of scheduling optimization, you can see that lots 6, 7, 8 are anticipated to come in, and what you can do then is assign these lots more optimally like this, and now you have a total cycle time of 6 hours and tool 1 utilization now approaching 100%. And so this is the kind of problem where we think a quantum computer can help with. We have not actually applied a quantum algorithm to this particular problem. We've done something similar to it. This is work that we do with Hyundai Corporation, where we're doing a multi-objective optimization problem. This is actually more complicated in that we're optimizing both route and scheduling at the same time. In the problem that we worked on with Hyundai, we have a depot here. and we're delivering packages to customer 1, 2, 3 in certain time windows. The packages are delivered by electric vehicles, and I think this maps fairly directly to the production scheduling problem I just talked about in semiconductor manufacturing, where you can think of customer 1, 2, 3 as tool 1, 2, 3. These electric vehicles as lots of semiconductor wafers traveling around in certain routes, and they could be going to, say, a dep tool and then an etch tool. I mean, a dep tool and then a litho tool and then an etch tool. And what we found was, looking at this problem, is that as you increase the number of locations, the number of binary variables increases quite rapidly. And the optimality gap also increases. The optimality gap is the difference between the theoretical best solution and the solution that the solver actually finds. We use Cplex here for the classical solver. And up to 15 locations, you get a pretty small optimality gap, 0.003%. So it's performing quite well. At 100 locations, though, you start to see an optimality gap of 15%. And so this is where you start to see where a quantum computer can start to fit in. If a quantum computer can find say, a 1% or 10% or 15% better solution, then this is worth quite a bit of money in semiconductor manufacturing. The number of variables in order to do 100 locations is about 14,000. So 1% to 10% is somewhere in the high thousands, low, maybe 10,000 number of variables. And the way these map to quantum computers is approximately 1 variable per qubit. And so we need about 10,000 qubits, probably logical qubits, in order to start to get, for example, 15% improvements in, for example, in this problem. Where we are right now is that we're expecting quantum computers with 1,000 qubits. We've already demonstrated one in the lab. We expect one to be publicly available in our systems by the end of this year, and that's probably where we'll stop for a while. And the 10,000 qubit machines may be available in sort of the 2029 timeframe in the future.
There's a really quick question on this one. When
yes.
you say 15% improvement on the
yes.
optimality gap, are you talking about the percentage points or
Correct.
percentages on the percentage?
For 15%.
15 percentage points, it would be then 0.651?
No, I'm sorry. The difference between the result that the that Cplex returned minus the theoretical result divided by the theoretical result is 15%. So there's 50% room between the classical solver and the theoretical result.
Okay. Thanks.
Okay. Yep.
2 percentage points or so. Okay.
Yeah. Any other questions I can take?
Real quick question. When you talk
yes.
about the 1,000 qubit machine and 10,000 qubit machine in the far future,
yes.
are those error corrected qubits, or how do you define that?
So good question. So we expect 1,000 qubits that we call physical qubits, so not error corrected.
Okay.
And then let me back up a little bit to just baseline everybody. I think probably the biggest challenge we face in quantum computers right now is the noise and the error rate in quantum computers. And right now we're using physical qubits. So one physical qubit corresponds to 1 qubit computationally. And and they're short-lived, they're noisy, they're not ideal qubits. There is a technique, though, to combine multiple physical qubits to create logical qubits. Logical qubits are now ideal qubits. They are long-lived. What we're doing is we're correcting the errors that occur in real time. And so we're expecting 1,000 qubits this year. In 2029, we're expecting 200 logical qubits, and I'll show you a roadmap of our plan for our hardware in the next couple of years. But so we'll be expecting 200 logical qubits in 2029, which corresponds to approximately 10,000 physical qubits.
Great. Thank you.
With that, yeah, you're welcome. Any other questions I can take? Okay, I see we have 8 minutes, so let me go through my other areas. So Lynn,
maybe a quick question. Sorry about that. So
go ahead.
When you say 1,000 qubits, because typically today all the qubits, they are not like fully connected. So when you have 1,000 qubits, and then for all the entanglement, everything to propagate, is there a coherence time problem in addition to the noise problem when you have more qubits?
So when we talk about noise, that includes decoherence effects. So we do have both, but we usually include them in a single metric.
Okay, thank you.
You're welcome. So in linear algebra, this is probably the area that at least most engineers I talk to are most excited about, because the largest computational loads we have are often solving large systems of linear equations like finite element analysis and circuit simulation and computational fluid dynamics. There in these, for example, in circuit simulation, if you look at sort of the workflow in SPICE, this center box here is nested inside a triply nested loop for transient analysis, and inside this loop is you're basically doing matrix inversion. So you what you start at the top of this box is a matrix A multiplied by X, which is your solution vector, and equals B. So A captures your circuit, B captures your constraints, and X is the set of all voltages and currents in your system. In order to find X, you need to invert A and multiply by B. So what you're doing here in this step is matrix inversion. In matrix inversion, if you look at the number of computational steps versus the size of the matrix, the classical solvers have a scaling that looks something like this. This is a log-log plot. So this straight line is polynomial lines. There's a quantum algorithm that has this kind of scaling. It's a logarithmic scaling, so it's quite different from classical scaling. And one way to interpret this curve is that say 1,000 node circuit can be, or a trillion node circuit, say, it can be, the matrix can be inverted in not too much longer time than 1,000 node circuits, where we know that this is not true for classical solvers. And so what we're saying is that this essentially is a way to decouple the size of the system from the runtime of the system. And so this difference is literally an exponential decrease in the number of computational steps. And the impact here could be quite enormous. Now, in the first slide, I showed you that linear algebra is probably the longest term application area for quantum computers. And the reason why is because the full end-to-end workflow has not been figured out. The way you typically think of using this matrix inverter is there's a classical computation that prepares a matrix, you pass it to a quantum computer that does the inversion, and then you pass it back to a classical computer. These classical to quantum and quantum to classical interfaces are quite low bandwidth, and just in the interest of time, let me just say that these are so slow that it would negate any theoretical improvement or acceleration by a quantum computer. So there are some interesting ways to approach both of these. Let me show you one way that is very interesting in my opinion. This is a paper published by Toyota, executed on and demonstrated on our quantum computers. They use a particular design space, a topological design space, and what they show is they can essentially solve the input problem by not loading a particular design, but by loading every design. And in their design space in this case is this 6 lines, the 4 lines that form the edges and the diagonals of this square. And what they're looking for is they're looking for the structure that has the best thermal conductivity. And the way you do this classically is you identify a candidate structure, and then you calculate its thermal conductivity, and then look at the next one and calculate its thermal conductivity, and so on and so forth. In the quantum method that Toyota developed is they can look at all 2 to the 6 or 64 structures simultaneously and then extract the optimal structure. And so what they're doing here is they're getting around the input-output problem by essentially asking a different question to the quantum computer than you would ask a classical solver. Instead of asking what you're asking the classical solver is what is the current and voltage of every node or between nodes. What you're asking the quantum computer here is what is the best design. And then the quantum computer outputs the best design, and then what you can do is go back to the classical computer and run the simulation on the best design and get, you know, the temperature at every point, or the voltage in circuit at every point, or whatever. Okay, so let me cover my last section, which is the nearest term application area, which is chemical and material simulation. This is new materials that often result in the highest jumps in cost performance curves. An example here is displays. We're working with Mitsubishi Chemical on modeling OLED light emitters that have 100% internal quantum efficiency versus standard light emitters, which have 25% internal quantum efficiency. So a 4x jump in efficiency. We're also working with Mitsubishi Chemical on advanced batteries. You can see most batteries, this is energy density here. Most batteries have an energy density that's an order of magnitude or less compared to, say, gasoline. But there is one battery chemistry that has an accuracy approaching that of gasoline, which is lithium air. But lithium air has quite a few development challenges in order to become practical. At any rate, we model this reaction within the lithium air battery. Our results are the red and green lines here, and the exact solution is the orange dotted line. And you can see we're getting pretty good at modeling these. This is actually pretty old. I think it's from 2021, and we're actually quite a bit more accurate, although on this scale it's hard to see. Anyways, if we think about applying this to microelectronics and semiconductors, one of the biggest problems we face is the interconnect delay. You can see back in 180 nanometer node, the delay due to the interconnect versus the transistor gate delay, there was a crossover, and now interconnect delay actually dominates transistor gate delay and overall delay performance. In fact, it was at the 65 nanometer node where we see microprocessor operating frequencies hitting its limits and has remained roughly at 3 gigahertz since. And so a way to, what we're trying to do here, for example, is find a way to slow down the growth of this delay. This is the projected curve. This is what is desirable. And the IRDS in their roadmap identifies the need for some new metal, non-copper metal. Ruthenium is the lead candidate. In DRAM technology roadmaps, ruthenium is also identified as a new material needed. And so ruthenium is an interesting material to develop, but it takes a long time to develop new materials. As a point of example, hafnium dioxide, from the first paper on using it as a gate dielectric in 1975 to the first time it was available on microchip in 2007 was 32 years. And so if one was going to develop a ruthenium ALD process, there are a number of interesting ruthenium precursors. Which one is the best? I just took 6 that have the prettiest pictures. It's not clear which one is the best. And you can go through the lab, and a lot of these are toxic, carcinogenic, explosive, and they're nasty materials. And you can go through all that, and you try it in the lab and find that it doesn't work. The problem is that reaction.
If I may just inject something. It's 11 o'clock sharp. Since we stole 5 minutes from your time, can you conclude in 5 minutes? Because
yes, let me conclude in 5 minutes. So let me say that this is where we think that quantum computers will make the nearest term impact. We are now at the point where we can do at the edge of what classical is able to do, which is simulate transition metal molecules. In a digital twin, what we see is basically simulating manufacturing processes such as silane PECVD, silicon PECVD, and we see a transformation of materials development from an empirical discipline to a computational one, which will accelerate materials development. This is our roadmap. Let me just jump to the punchline. We're here in 2025. We see the first applications here in sort of the 2027, 2028 timeframe, and we see error correction with 100 million operations happening in 2029. And so this is 4 years away now. These are our recommended actions. If you have first establish a strategic plan, your strategic plan should take into account the arrival of quantum error correction in 2029, an expected supply-demand mismatch we see coming in quantum computing, and the worldwide talent shortage. Evaluate your quantum opportunities through proofs of concepts. First, this means identifying your quantum opportunities. Most people don't know what they are. Also, through developing proofs of concept, you will develop quantum capabilities which will help address this talent shortage. Join a quantum ecosystem that'll give you access to hardware, knowledge, and software development. And lastly, start today. The learning curve is steep. Organizations that start in 2025, it takes about 4 years. You can intercept quantum error correction in 2029. And that's my last slide. Okay, so let me stop there.
Thank you very much, Chuck.
Yes, you're very welcome.
It's extremely interesting. Unfortunately, we don't have time for last-minute questions, but we ask many questions during the talk. So I have 2 requests to you. Can you share the slides to me, and I would share them with the audience in post on the website.
Yes, I'd be happy to.
And we are going to post the recordings of this on the MAPT website as well.
Great, terrific.
Okay, thank you very much.
You're very
thank
welcome.
you all. Thank you, Chuck, and thank you all. And it was a great deep dive and great meeting. So we